Hello all, welcome back to Chapter 2 Solutions chapter. In this video, we will cover vapor pressure of solution till non-ideal solution. So let us begin with this video. Vapor pressure of solution. Consider a binary solution of two volatile liquids A and B. When the solution is placed in a closed container, both the liquid vaporizes. Eventually, an equilibrium is established between vapor and liquid phases. Both the components are present in the vapor phase. Pressure exerted by each component in equilibrium with solution is called as a vapor pressure of that component. Since two components are involved, each component's pressure is partial pressure and the sum of their pressure will give the total vapor pressure. The partial pressure of the components are related to their mole fractions in the solution. This relationship is given by Raoults Law. Let us see Raoults Law. It states that the partial vapor pressure of any volatile component of a solution is equal to the vapor pressure of the pure component multiplied by its mole fraction in the solution. For this, if we have considered a binary solution of two volatile liquids A and B having partial vapor pressures as P1 and P2 with X1 and X2 are their mole fractions in solution. Then, according to Raoult's law, we can write it as P1 equals to X1 into P1 naught, and for second solution P2 equals to X2 into P2 naught. Here P1 naught and P2 naught are the vapor pressures of pure liquids A and B respectively. According to Daltons law of partial pressure, total pressure is given as a sum of the partial pressures of the two components. So P equals to P1 plus P2. But from Raoult's law, we know that P1 is equal to X1 into P1 naught and P2 equals to X2 into P2 naught. Substituting the values in the equation, we get P equals to X1 into P1 naught plus X2 into P2 naught. Since X1 mole fraction of the first component is equal to 1 minus X2 mole fraction of the second component, so the above equation can be written as equal to P1 naught into 1 minus X2 plus X2 into P2 naught, which can be written simplified as P1 naught minus P1 naught into X2 plus X2 into P2 naught. Again, on simplifying more, P2 naught minus P1 naught into X2 plus P1 naught. When we plot a graph between pressure versus X2, a straight line is observed. For this, we will see the graphical representation. In this graphical representation, there is a plot of vapor pressure versus mole fraction. It is actually a combination of two graphs together and which is given in the combined form here. So it appears this way, which is being shown here. Now the plot of pressure total versus X2 mole fraction is a straight line, which is represented by the third curve. The plot of P1 versus x1 and P2 versus x2 are straight line passing through the origin, which is represented by the dotted lines by curve 1 and curve 2. When x1 is equal to 1 and x2 equals to 0, the pt is equal to p1 naught, and when x1 is equal to 0, x2 is equal to 1, total pressure equals to p2 naught. So these are shown by the lines 1 and 2 shown in the graphical representation. Let us see the composition of vapor phase. The composition of vapor in equilibrium with the solution can be determined by Dalton's law of partial pressure. If Y1 and Y2 are the mole fractions of two components in the vapor phase, then we can write P1 equals to Y1 into P and P2 equals to Y2 into P, where P1 and P2 are the partial pressures of two components in the vapor and P is the total vapor pressure. Since till now we have studied about Raoults law, now it's important to know about which type of solution Raoults law is applicable. So let us study about ideal and non-ideal solutions. First, ideal solutions. Ideal solutions are those which obeys Raoults law over entire range of concentration. Secondly, the enthalpy of mixing is zero. That is, no heat is evolved or absorbed when two components forming an ideal solutions are mixed. Third, there is no volume change when two components forming an ideal solutions are mixed. Thus, volume of an ideal solution is equal to the sum of the volumes of two components taken for mixing. Next, in an ideal solution, solvent-solute, solute-solute, and solvent-solvent molecular interactions are comparable. The vapor pressure of an ideal solution always lies between vapor pressure of pure components, as it was. For example, solution of benzene and toluene behave nearly as an ideal solution. Perfectly ideal solutions are uncommon. Let us see another type of solutions, non-ideal solutions. These solutions do not obey Raoults law over entire range of concentration. Secondly, the vapor pressure of these solutions can be higher or lower than those of pure components. The deviation from the Raoults law. The solution shows two types of deviation from Raoults law. First, a positive deviation, and second, a negative deviation. Let us first see positive deviation from Raoults law. The solution in which solute-solvent intermolecular attraction are weaker than those between solute-solute molecules and solvent-solvent molecules exhibits positive deviation. The vapor pressure of such solutions are higher than those of pure components. Graphical representation. Example, solution of ethanol and acetone. Second, carbon disulfide and acetone shows a positive deviation from Raoults law. Second, negative deviation from Raoult's law, the solution in which interaction between solvent and solute molecules are stronger than solute-solute or solvent-solvent interaction exhibit negative deviation. The vapor pressure of such solutions are lower than those of pure components. Graphical representation for negative deviation from Raoult's law. The thick lines represent the vapor pressure of the solution, which is showing a negative deviation from the ideal behavior, which is being represented by the dotted lines. Example, solutions of phenol and aniline and chloroform and acetone shows negative deviation from Raoult's law. With this, we complete the topic. Thank you for watching the video.